All right, guys, so we have chapter 2 here, which is basically on one-dimensional linear motion. That means in this chapter, we're going to be studying how to understand one-dimensional motion, how to solve problems in one-dimensional motion, using the equations that we're going to develop, using the graphical methods that we're going to learn, or we learned also in the previous chapter, plus add new concept, new materials that will help us to understand things in future chapters. All right, so let's dive into. So we have talked about motion last chapter. We talked about how we can represent motion diagram to help us understand graphical way of looking at the motion. And you can think of, like, let's say right now, this one-dimensional motion can be, and technically any type of motion, right? Could be two-dimensional or three-dimensional. You can break it down into two types, a uniform motion and a non-uniform motion. And the differences between those two type of motion is that uniform motion is when object moving at constant velocity, right? So you can say constant speed or constant velocity, but the idea here is if you are looking at, remember, those are positions, right? X1, X2, X3, X4, and so on and so forth. The distance between each frame, right? Distance between, let's say, frame 1, frame 2, which is, again, in terms of t equals 0, 1, 2, 3, 4, and so on and so forth. So all those distances are the same, or you can say all the displacements are the same. That means equal displacement during the equal, time intervals, which means since the velocity is displacement over time, that means all those velocities also, those green arrows, right? So the green arrows actually represent displacement. But remember, if you divide that by 1, you're basically getting a velocity with the same, magnitude and direction vector. That means all the vectors are identical in terms of their direction and magnitude. So we can say that this is a uniform motion. That means uniform motion is a type of motion where the object is moving at constant velocity. All right. Here's an example. The position of a runner as a function of time is plotted as moving along the x-axis of a coordinate system. During the 3-second time interval, the runner's position changes from x1 equals 50 meters to x2 equals 30.5 meters as shown. What is the average runner's, what is the runner's average velocity? Right. So remember, we talked about a velocity equation last time, v average, and this was then your displacement over time, delta x, delta t. All right, so then delta x is the difference between your position, right, x2 minus x1, and this delta t we're given as a 3-second, which is the time interval. Now, this means then what we have here is the displacement, divided by time, which will be, let me do it here, the average equals then 30.5 minus 50, there are in meters, and then this is divided by 3 seconds. All right, so if we calculate, we will get then negative 19.5 meters, that's my displacement, divided by 3 seconds, and this is negative 6.5 meter per second. Now, what we get here is, remember, the velocity is a vector, so you have then 6.5 meter per second, the speed, negative is then in which direction you're moving. So then you can say, all right, so this is my x1, this is my x2, and going from x1 to x2, on average, the person was running at 6.5 meter per second. And if the person moving at constant velocity, then technically you can say then v average is equals to v, because at any time, the velocity is the same for, let's say, if you talk about, 1 second time interval, another 1 second time interval, another 1 second time interval. Maybe, for example, for this particular 20 meters, runner can actually run at constant velocity. So this will be basically your velocity which will be, let's say constant. It could be in terms of this problem. All right, so one of the things then we can do, for example, if you have somebody moving along the x-axis and you measure the distance, you measure the or displacement, and you measure the time, you can then take the data and plot in a position versus time graph, right? So these are the graphs that we call them position versus time. And position versus time. So all of these graphs, let's say in this case, position versus time graphs, will have the position on the x-axis, on the y-axis, and the time on the x-axis. Generally, any type of graph that is, as a function of time, that means you're plotting it in terms of as a function of time, time always goes on the x-axis. It's horizontal. So imagine then this is the data that you plotted. And what we have here is, if you then take any 2 points, so let's say here's 1 point, and let's say here's another point, right? And let's say you find the slope, which is, rise over run. But let's do this, for example. So let's say we have this first time interval. That means this is, our first going from t equals 0 to t equals 1. Let's say if I take this and I do rise over run, then my rise is nothing but, since it's x-axis, right? Nothing but delta x. And my run is nothing but delta t. That means this is basically the time interval, the velocity during that first time interval. So let's call this v1. And let's say do the same thing for this then time interval, and then the other one, and then the other one. And what we will see here is that v2, v3, v4, v5, right? All of those velocity is, you can find by, finding the slope. Because slope of the, you can see, right, position versus time graph is nothing but your, average velocity. But if I look at this, right, say look at this v1 and v2 and v3 and v4 and v5, if I compare them, one thing I will see here is that they are all equal to one another. All equal to one another. That's because the line is a straight line. And in a straight line, if you have, calculating the slope doing for different intervals, you're going to get the same value. Now, what does it mean when the velocities are all the same? Well, it means that object had exactly same velocity for this 0, 1, 2, 3, 4, 5, let's say, or so seconds. That means for that 5, 6 seconds, velocity did not change. What does it mean? It means it's a uniform motion or constant velocity motion. Uniform motion means that object moving at constant speed in a straight line, and the graph for that will always look like this. You can say that this is how the uniform motion graph will always look like. All right. That means if you have some position versus time graph and you get a straight line like that, that's a uniform motion. That means you have now 2 ways you can recognize uniform motion. If, for example, those motion diagrams give you, points that are equally spaced, that's a uniform motion. When you have a position versus time graph and you have a straight line like this, that's a uniform motion. And you always can say that, the slope of the position versus time graph will always give you the velocity. All right, so now one thing we can do is we can set up one equation to describe how the object, let's say, changes its position as a function of time moving with the uniform motion. Because one thing we got here is this. So let's say I have V average equals delta, and I'm going to use S instead of X or Y because S is like a general. So you can use also R technically. So delta S over delta T. Now, if the motion is uniform, then there is no such thing as V average because all the velocities are the same. Remember, you can find the average mathematically by taking V1 and V2, adding them together and divide by 2, for example, right? So, but let's say this is 10 and the other one is 10. And if you divide by 2, that's 20 over 10. Again, it's 10. That means the average is same as all the values. That's right. The average is the same if you have a uniform motion. So technically I can just say it's Vs. S means just along that s axis, for example. That means velocity, doesn't have to be average anymore. It's a constant velocity. See, if I rearrange this, I can say then delta S is equals to Vs times time, or delta T, right? Moving the delta T to the other side. Remember, the delta S is S final minus S initial. So then imagine, and this is equals to V times T. So if I move the S initial to the other side, then we get this equation for the calculation of the final position of the object. That means this equation, where the final position equals initial position plus speed times time, this only works for uniform motion because we are assuming that the speed is, uniform. Speed being uniform, then you can say, all right, so let's say I start from the position 0, and let's say I move at 10 meters per second for 1 second. What is my final position? Well, it's 10 meters because you are moving at 10 meters each second. Remember, speed tells you how many meters each second you cover. What if you go 2 seconds at that speed? Then your displacement is final position is 20 meters. How about for 3 seconds? Well, 30 meters, and so on and so forth. That means there's a linear relationship in terms of that. All right. So now let's summarize what we learned last time as well in terms of some of the scalar and vector quantities. The distance an object travels is a scalar quantity, independent of direction. Because if you are here at x equals 0, if you move 10 meters to get to this point A, your distance is just 10 meters because you walked 10 meters to get to point A. Even if the point A is on the left side, so technically to get to that, you still have to travel 10 meters, right? That means, this is just in terms of how much distance you're traveling. Displacement of an object is a vector quantity equal to the final position minus the initial position. Well, this one is a vector quantity because let's say if, for example, A here happened to be on the right side, you have to move then to the right to get to that. If you move to the left, you will not get to that point A, which is your destination, let's say. So displacement is a vector which is always given as final position minus initial position, which also then ends up being either positive or negative depending which side you're moving. Speed is information about just how fast you're moving, and it's a scalar quantity, again independent of direction. Velocity, on the other hand, is a vector quantity. It tells you how fast you're moving and in which direction, right? So in which direction. Now, the speed is the magnitude of the velocity vector, all right? So let's say if here's a velocity vector, so then v written as a speed, then this is basically magnitude of the velocity vector, and then you have the direction. And direction, I can do it different ways. So for example, I can do, let's say, I hat, which is the unit vector. So that means this is basically just a horizontal velocity in a, I hat direction. Or it can be also Vy, J hat, and things like that. But these are, let's say, two-dimensional. So right now we're just keeping one-dimensional. So let's say I can just, write it like that, right? So anyway, we'll learn about this in chapter 3. But this is in terms of right now, I can write like this. So V here is, remember, our velocities can be one-dimensional in this chapter. So I can just say X, meaning that this is horizontal. So if I put 3 meters per second, if I put plus 3 meters per second, that means this is an object moving to the right at 3 meters per second. Well, if I put it negative 3 meters per second, this is an object moving to the left at 3 meters per second. That means the plus minus here just representing which direction our object is moving. So an object that is speeding up or slowing down is not in uniform motion, which means, like, let's say then the speed is changing as a function of time. Obviously, it's not a uniform motion because uniform motion means that you never change your speed and you never change your direction. But right now, we're not worrying about direction in this chapter. We're going to leave it up, for chapter 3 to worry about the direction. Here, we're just talking about if you are not moving in a uniform motion, that's because you're speeding up or slowing down, okay? That means what I have here is, for example, if you have an object is here moving with the initial velocity of 5 meters per second to the right. Let's say 1 second later, the velocity here, final velocity is then 8 meters per second to the right. Means that now I have a change in velocity. And this is an example of something that is speeding up, right? Because you increase the velocity. Means as a function of time, velocity increases. So then motion diagram will look like this. So here's the velocity between time 0 and 1. And then here's the, the motion diagram for the second time interval. And this is a third time interval. And this is a fourth time interval. And you can see, right, if I draw those vectors, you can see, right, they're increasing as a function of time, which means it's a, speeding up process. You're going to the right and you're increasing your speed. All right, how about the position versus time graph? What will happen to the position versus time graph? Well, remember, this is a uniform motion. But once you have a non-uniform motion, then you can no longer have a straight line. Then your line will actually change. It will always then have a curvature. This is you speeding up. Okay, speeding up, moving to the right, speeding up in a positive x direction. This is you slowing down. So, or like this, or like that. Slow down in a positive x direction, and so on and so forth. So for example, then this would have been speeding up in a negative x direction. This, slowing down in a negative x direction. But that's what you will have. You will always have a curvature. You will always have a curvature. We'll talk about that a little bit more. But for now, one thing we can do here is this. So let's say if you have a particular, let's say a graph where the object is speeding up, then let's say your graph will look like this, right? So it will be curved like that. Okay. So what do we do here? How do we find velocity? Well, remember, velocity here is changing. So there's not a constant velocity. So we can find average velocity. So for that, what we do here is we choose any 2 points of interest, right? So this is for this time final. Let's say this is for this time t initial. And then I can say, all right, so those are my 2 points. And then I can draw this line, which basically connects those 2 points. Now, I don't know if you guys know the name of this type of line or not, but this is the line that gives us average velocity. And this is known as a secant line. Okay, so the secant line which connects 2 points in my curved graph, right? So secant line gives you the average velocity, because then what I will do here is I will find the slope of that by doing average, a rise over run, which is delta x over delta t. So this is my delta t, and that's my delta x, right? Delta x over delta t is my average velocity. Okay, so that means we will have that. Okay, so then you also gonna see that we can calculate something else, which is basically velocity at some instant of time. All right, so but in any case, so here's what we have. If I want to know the average velocity, I use that secant line. But if I want to know velocity, let's sort of go back over here for, let's say, velocity at this instant of time, then I can do a tangent line. So kind of tangent that is tangent to that point. Then this will be, my instantaneous. You can write the instantaneous velocity is the object velocity at the single instant of time. So the average velocity, delta s over delta t, becomes a better approximation to the instantaneous velocity as the delta t gets smaller and smaller. That means for my graph, right? So if I have this graph, so this is my curvature. So if I finding the average velocity between those 2 points, then I'm going to get, average velocity using the secant line. I imagine this is my, delta t, right? But see, if I then draw this line, my delta t gets closer, smaller. This one, my delta t again gets smaller, and even smaller until I finally have this where my delta t basically approaches 0. Delta t approaches 0, not t. Delta t approaching 0 means that my time intervals are extremely small. Then my graph is represented by, sorry, not the graph, but let's say the slope, right, is basically in terms of the tangent line. And the slope of the tangent line, that will give me that instantaneous velocity. And mathematically speaking, the instantaneous velocity is going to be the derivative of s as a function of time, ds dt. All right, so remember, this is then the equation for the instantaneous velocity, which is the limit where the delta, the delta t approaches 0 for the ratio of delta s over delta t. And this is basically the graph that I just mentioned in terms of the always, right? Your graph will be a curved graph like that. And second line will give you the average velocity. But as you kind of decrease your delta t and make it approach to 0, then your graph will, actually end up being a tangent line. And the tangent line will then give you the instantaneous velocity. That means every time you have position versus time graph, you can use the tangent graph, right, tangent line to figure out the velocity. All right, so as delta t continues to get smaller, the average velocity, that v average equals delta s delta t, reaches a constant or limiting value. The instantaneous velocity at time t is the average velocity during the time interval delta t centered on t, right? So you remember, right? So this is basically derivative of s with respect to s. And since this is a class where the CAC1 is a requirement, I imagine most of you already know this, right? So that means you can take the derivative of, let's say position as a function of time. So let's say if you're given this, for example, x equals, 3t squared. That means x changes as a function of time. You can see, right? So what is position when t equals 0? Well, the position is 0. What is the position when t equals 1 second? Well, position is 3, right? 3 times 1, so it's 3, and so on and so forth. Then for the velocity at any instant of time, you can take the derivative of this guy, with respect to t, which will be then 6t. Hopefully you understand, how to do that, right? So it will be 6t. Then you can say, right, so then what is the, velocity when, for example, t is equals to 2 seconds? Well, this will be 6 times 2, so then 12 meters per second, and so on and so forth. All right, so this is again that v is the slope of the position versus time graph at time t. So most of the time then we are going to be working with instantaneous velocities. So when we start, going through, let's say, kinematic equations and things like that, I don't really go over in terms of the average velocity. I'm mostly going to talk about, let's say, instantaneous velocity. What is the velocity at, let's say, at the initial time? What is the velocity at the final time? Those are technically instantaneous velocity for those specific times. All right. Also, you can combine motion diagram and position versus time graphs into like better understanding the motion. All right. So, for example, let's say here's a position versus time graph, right? And let's say we want to know what's going on over there. So if you see that particular diagram, right, that particular graph, you should be able to sort of like read and understand what's going on over there. Because one of the things we have here is this. Vertical axis is the position. So then what we say here is that at t equals 0, you can see, right, this is t equals 0, we are at position A. But position A is below the t-axis, which means, let's say, if I'm doing, like, let's say, the Cartesian coordinate, position A will be to the left of the origin, somewhere over here. This is, TA, which is, the time at position A. And we take that to be t equals 0. And what I have here is this. See, the graph look like this, right? So this graph always, that shape always represents increasing speed, moving to the right. Remember, right? Just like I mentioned. One way we can figure out here is this. See, at point A, I do a slope. See, even if I don't know any values to calculate the slope, I know one thing. This slope is positive. That means velocity is positive at point A. Positive velocity means at point A, we have a velocity to the right. That means we will be moving to the right. Now let's say we get to point B. Point B here, you can see, right, at the origin. That means we're going from point A to the origin. We're moving toward the origin. What I have here is, if I draw this, tangent line at point B, I can see another thing is that, well, my slope will be again positive. That means at point 0, right, at point A, x equals 0, we are still moving to the right at point B, let's say. We're still moving to the right. But the slope is steeper than at A, which means we are moving faster. Steeper the slope, faster the speed. All right, then you should recognize this shape, which again, I showed you that that's a decreasing speed moving to the right, which means by the time we get to point C, which is some, to the right of the, origin, right? Let's say somewhere over here, right? We will have, look at the graph, right? It'll be a graph shaped like that. What is that? Well, if I do a slope at point C, well, there is no slope. I'm going to get 0, which means the speed is 0, which means at point C, we actually stop. So you can see that's why there's no speed at point C, right? V equals 0. And then what happens here is, you can see, right, then after that, the graph look like that, which is an example of speeding up to the left. That shape is speeding up to the left. Now, what it means is then we go from C to D, and let's say if I do the slope at point D, I can see that since at C I had no speed, but at D I have a speed, but that speed is going to be negative, right? I mean, the velocity will be negative because my slope is negative. That means that from point C, I'm going to turn around and start moving to the left. Then go to this point D, and then basically I'm moving with some negative velocity. Negative velocity means just basically moving to the left. Then going from D to E, my graph has this shape, which is actually slowing down moving to the left. Why? Because when I do the slope at point E, I'm going to get less steep, which means, speed is decreased. So that means by the time I go from, D to E, I will be then slowing down, right? So that's why this graph can help you along with the motion diagram to understand what's going on. All right, so let's then do some example. So this example, again, will be in terms of using the derivatives. And remember, so let's say I have some, there's appendix in the book, and there's some, let's say slides that I have also that gives you some of the review. But, since I expect you guys to know that, I'm going to skip that, going over that. So we have a jet engine. The jet engine moves along an experimental track, which we're going to call x-axis. We will treat the engine as if it were a particle. Remember, using a particle model because we can ignore any type of size for the jet engine. We don't care about its size or shape. So its position as a function of time is given by the equation x equals at squared plus b, where a and b are some physical constants. A is 2.1 meter per second square, b is 2.8 meters. That means what I have here is this, right? So my x as a function of time is equal to a times t squared plus b, right? So again, a is 2.1 meter per second square, and b here is 2.8 meters. Now, determine the displacement of the engine during the time interval from t1 equals 3 seconds to t2 equals 5 seconds, right? That means we want to know what is the displacement, right? Now, what we do here is this. For displacement, remember, displacement is delta x, which is x2 minus x1. All we need to know what is x2, what is x1, and then we can find the difference. Let's look at x1. x1 is when the object is at t equals 3 seconds, which means it's a, which is 2.10 meter per second squared times 3 seconds squared, then plus 2.80 meters. Okay, so if I calculate this, I should get 21.7 meters. Then I calculate x2, which is position at 5 seconds. So this will be 2.10 meter per second squared times 5 seconds squared plus 2.8 meters. And I'm going to get 55.3 for this. Now, what is the displacement? So I come back here and I do 55.3 meters minus 21.7 meters. And this is going to give me 33.6 meters. That means that's my displacement for part A. All right. Part B, it says determine the average velocity during this time interval. let's see what we do for average, how we can calculate the average. Well, for average, well, V average is nothing but delta x over delta t, or displacement over time. Well, remember, my displacement is 33.6 meters, and my delta t is nothing but 5 seconds minus 3 seconds, right? Which is just 2 seconds. That means this is going to give me 16.8 meter per second. That means on average, the jet was moving at 16.8 meter per second. All right. Part C, determine the magnitude of the instantaneous velocity at t equals 5 seconds. All right, so let's see what we do. How do we do that? All right, so for part C, what we do is this. Remember, we want instantaneous velocity. So then we take our x and take the derivative of that to have a function of, and for the velocity as a function of time. So this will be then taking the derivative of at squared plus b. So remember, now you are taking first derivative of at squared, and we're going to get then, let's say, 2 times at, and then plus the derivative of b. But b is a constant. It doesn't depend on time, so it's nothing but 0. Right? So we can just basically ignore that. That means our v as a function of time is equals to 2 times at. Then using this, I can say v when t is equals to 5 seconds is equals to 2 times 2.1 meter per second, then times 5 seconds, which is for the time. All right. So if I do that, my velocity at t equals 5 seconds is going to be 21, because 2 times 5 is 10. 10 times 2.1 is 21 meter per second. And that's my final answer for this part C. All right. And you can see, right, if I plot this, you're going to get a graph like that, right? You're going to get a graph like that because it's a non-uniform motion. So it's going to be curved, and we are speeding up to the right. So that's kind of what we have. It's important that you guys, let's say, remember the shape of the graphs. So when you're speeding up, when you're slowing down, in which direction and how the graphs will look like. Remember, speeding up in a positive x direction, speeding up in a negative x direction, slowing down in a positive x direction, slowing down in a negative x direction. Right? Those can help you sometimes to better understand what's going on. All right. So one of the things we have here is this. So let's say I have a graph, position versus time. And remember, so let's say I have something like this. So I can use that graph using, let's say, the slope at any instant, right, to construct actually velocity versus time graph. All right, so velocity versus time graph. So for example, you can see, right, so it's 0 first and then increases, becomes steeper and steeper and steeper. That means my graph will actually look like this. This will be my velocity versus time graph. And this means that velocity increases, right, as a function of time. This doesn't mean there's a, this is for a non-uniform motion. The graph for the velocity versus time, if it's a uniform motion, will be something like this. Velocity doesn't change as a function of time. So this is uniform motion. And this is how non-uniform will look like. All right, non-uniform motion will look like. All right, so, but also this is what one thing we can do. So let's say if I take this velocity versus time graph, and from the T1 to T2, let's say, I want to know how I can, let's say, take this velocity versus time graph and use this information to find the displacement. Right. And one of the things I will have here is this. So if I take this velocity equals dx dt, first then I multiply both sides by dt. So I'm going to get vs dt equals dx. And then if I integrate both sides, as you can see, right? If I integrate both sides, then what I will have here is this. On the left side is from x1 to x2, integral of dx, which is nothing but delta x. On the left side, then I have an integral of vs dt, and this integral is nothing but the area here under the velocity versus time graph. And that's what we have. You can see, right? And then let's say what I get here is area under the position versus time graph for the, uniform or even non-uniform motion, right? Area is equals to my displacement. So it's kind of go other way around. Going from displacement to velocity, you do the slope, take the derivative. Going from the velocity to displacement, you find the area under the graph, which means you integrate. Okay, so that's why this equation here is representing how to find your final position. This is actually just move the initial position to the left, to the right. So, but if let's say you move this in the other direction, this becomes just delta S, which is just equal to the integral of the velocity and time. Right. All right, so that's kind of one thing we have, right? So that means you know how to go from one direction to the other. Okay. That's because, for example, you can see, right, if you have a graph for the velocity versus time, then what you have here is, for example, for this one, what you can do here, you can break it down into small time intervals and just add the small, let's say, segments together, which end up being, giving you that you're just calculating the area under the velocity curve between T initial and T final, which is basically, mathematically speaking, nothing but the integral, right? Area of the graph is just the integral of the velocity and dt. All right, so here I have some, extra help for the integrals. And, again, I expect you guys to know all of this. So I will, I have the, this is as a reference, and the book has, like, let's say, some appendixes that, go over all of those things. But, just review this if you don't remember some of the rules for the integrals or the derivatives, but, they're relatively straightforward. All right, so now we are continuing with the non-uniform motion. Remember, this is still already, we are looking at the non-uniform motion. And non-uniform motion means that we have changing velocity as a function of time. And if you change the velocity as a function of time, that ratio of delta V over delta T is defined as the rate of change of velocity, which we call acceleration. And it's a vector, it's in the direction of the changing velocity. All right, so this is just gives you an example where you have two cars, Volkswagen Beetle and Porsche. And then let's say you find the velocity of each one as a function of time. And let's say you have the data set over here. And we plot that. One thing we will see here is that Porsche going to have a much steeper slope. The line for the Porsche will much steeper slope than, let's say, the graph for the Volkswagen. That's because it tells you that Porsche has a higher rate of velocity change than Volkswagen. So if we take then the graph of the velocity versus time, and then I find the slope of this, velocity versus time graph, right? The slope here is nothing but delta V over delta T, which is in a way is actually average acceleration. That means what we do here is if I have a velocity versus time graph, I can find the slope, and that slope represents, physically speaking, represents acceleration, which is the rate at which you change your velocity. Okay. So we have average acceleration, which gives you, let's say, how you change your velocity during some time interval. Could be 5 seconds, 20 seconds, 5 hours, or whatever, right? So that's basically what we get for the delta V, delta T. But obviously, we also can look at in terms of the instantaneous acceleration, where, let's say, if you have a velocity versus time, and let's say, for example, your velocity is something like that, right? So you can try to then find the tangent to this, and this will be then acceleration instantaneous, which is generally dv dt. Okay, so acceleration instantaneous in that direction, right? Going to be the derivative of the velocity as a function of time. Okay. All right, so we have more or less some, good idea, good understanding of what's going on with our motion. So you have an object goes from point A to point B, and as the motion that you are looking at, right, as it goes from point A to point B, we can find the displacement, which is, let's say, given in terms of delta S. And then if I find the time it takes to travel this distance, then I can find the average velocity, which is delta S over delta T, or at any instant of time, I can find the instantaneous velocity, which is ds dt. Now, if the velocity is constant, then what we will have here is, we can call that uniform motion. Okay, that means, for example, if I take this derivative and I have, let's say, 5 meters per second, right? So for example, I get 5 meters per second, that means it's constant. But if I get, let's say, 5t, that means it's not constant, it changes with time. So you have to understand, right? So if you have a uniform motion, that means you have a constant velocity. Non-uniform motion will include some kind of time dependence for the velocity. And if your velocity changes, then you can look at an average acceleration, which is the rate at which your velocity change, or instantaneous acceleration, which is, let's say, acceleration at some instant of time. So again, graphically, A average is the slope of the straight line velocity versus time graph. And if acceleration is constant, then acceleration AS is the same as average acceleration. And mostly we're going to be keeping, let's say, average, let's say, constant acceleration. That means most of the time it's going to be constant. Doesn't mean that we're not going to be looking at, let's say, changing acceleration, but most of the time we can keep it constant. So acceleration, like velocity, is a vector quantity and has both magnitude and direction. All right, so one thing we're going to do now is this. We're going to assume that we have, for example, a constant acceleration, and we're going to start deriving some equations that we can solve for any type of problems as long as the acceleration is constant, right? So this is basically known as the kinematic equations. You can see, right, the title. So kinematic equations with constant acceleration, which means we assume that acceleration is constant, then we develop these equations. The first equation actually is straightforward, comes directly from this. A is equals to delta V over delta T. Remember, is if A average, right? If the acceleration is constant, then A average is just A with a subscript S. Then I can just rearrange and say, all right, delta V is equals to an acceleration times time, or delta T. I usually write time because initial time we can always set to 0. Then Vs minus V initial is then equals to A times T. And then just move the initial to the other side, so it becomes V initial plus AT. And that's what we end up with this. This is going to be known as a kinematic equation 1, where final velocity of the object equals initial velocity plus the rate at which it changes velocity, so acceleration, then times delta T. All right, so this is going to be our first equation for the kinematics. Okay. Then we have the second equation. So second equation we can derive technically from the graph. And this comes from the fact that, for example, if you have velocity versus time graph, right? So you can basically take this graph and separate into two parts, right? Separate into two parts. So you have, one part where you end up, showing you that this is basically the displacement. The other one, let's say there's extra, let's say area where, you have, curved part, right? So, and putting them together, you end up with this equation for kinematics 2, okay? Which tells you that final position equals initial position, which in a way, think like this. This is basically the displacement is equals to initial velocity times time, then plus 1/2 times acceleration times t squared. But a lot of times we just move this initial position to the right and just write it like this. So solving for the final position. This is going to be kinematic equation 2, which allows you to find position or relate position, velocity, initial, acceleration, and time. You also have the third equation, which is, again, you can derive by, right now, combining those equations 1 and 2 and end up with this equation where final velocity of the object square equals initial velocity square plus 2 times acceleration then times displacement. This is going to be known, let's say, third equation, kinematic equation 3. All right. So that means you have now 3 kinematic equations. I have this is 1, this is 2, this is 3. So in class, I'm going to be referring to them in terms of their numbers. So let's say kinematics 1, kinematics 2, kinematics 3. So try to remember the order. I will also give you another one, which is fourth one. And this is basically for the delta S. And this is equals to V initial plus V final divided by 2 times time. This is also a useful equation because this is nothing but see V initial plus V final over 2. That's the average velocity, then times time. But here we're assuming that average velocity is not necessarily equal to the velocity at any time. This is non-uniform. Remember, this is non-uniform motion, but with A equals constant. That means with constant acceleration. All right, so let's summarize what we have. Motion with constant velocity, which is a uniform motion, means that position versus time graph going to be a straight line like that, where the slope is the velocity. And since velocity is constant, velocity versus time graph going to be like this. V will be horizontal, horizontal line. And since the acceleration is the slope of the velocity, then acceleration here is 0. That's how we can also define uniform motion. Uniform motion when displacement are equal for the time intervals, velocity is constant, the graph looks like a straight line, horizontal line is velocity is a horizontal line, and acceleration is 0. That means uniform motion automatically assumes that acceleration in the system is 0. That's why you're not speeding up or slowing down. That's why your velocity is constant. As velocity is constant, you're moving at uniform motion. Whenever you have a non-uniform motion, then your graph is a curved for position versus time. And then you can use that to see that velocity would change as a function of time. And if there's a velocity change as a function of time, you can find the slope of that, and that's what you get for the acceleration. All right. That means, in a way, to summarize everything, right? So this is what we have. For the kinematics with constant acceleration, we can use a particle model. With the particle model, we can always assume that we have object just going from some point initial to some final point. We don't care about any of its size and shape. We can use picture, we can use diagrams, we can use graph, right, to understand and describe the motion. And then we have those kinematic equations that we can then use, assuming if the acceleration is constant, that let's say, again, so this is non-uniform, acceleration is constant, so I can use those equations. Now, imagine if you kind of look at these equations, right? If the acceleration is 0, for example, then this is 0, and V final is same as V initial, then this term is 0, and you end up with this one, which was a uniform motion equation, right? And then if this is also 0, means that, again, velocity before and after is the same. That means you can say, right, in a way, this can be for any general motion. But if the acceleration is constant, you can just use them in these equations for non-uniform motion. If acceleration is 0, you can just simplify this and use it for the, uniform motion. All right, so let's look at some examples here. An automobile is moving to the right along a straight highway, which we choose to be positive x-axis. Then the driver puts on the brakes, and if the initial velocity when the driver hits the brakes is v1 equals 15 meters per second, and it takes 5 seconds to slow down to v2 equals 5 meters per second, what was the car's average acceleration? That means read the problem twice always and make a table like this. For example, what we're given here is this. we have an initial velocity of 15 meters per second. That means we have a car that is moving at 15 meters per second, and we don't care how long it was moving at that speed. What we care is this: when it gets to this initial position, or let's say when it gets to some point, it starts slowing down. It hits the brakes, and we then start looking at the motion from that point on. We then say, this is my initial position, x initial equals 0, or actually I'm going to put like x1 because I'm using 1 and 2s. So x1 equals 0, and then I can say then t1 equals 0. And then what I have here is, well, I run out of my room. Let me move it here. So let's say v1 is equals to 15 meters per second, v2 is equals to 5 meters per second, t1 is 0, t2 is equals to 5 seconds, and x1 is 0 because I use that as an origin. So that's what I'm given. And what I want to find, well, is the acceleration, average acceleration. Well, we know one thing. So let's say average acceleration, right? Average acceleration is, delta x over delta t. Okay, delta x over delta t. And in a way, let's say we can just use that equation, to calculate this. So let's say A average is equals to delta v over delta t equals v2 minus v1 over t2 minus t1. And so this is equals to 5 meters per second minus 15 meters per second divided by 5 seconds minus 0 seconds. And I'm going to get negative 2 meters per second square. Okay. So technically, I have 1 decimal point for all of those, so I should write it like this. By the way, meter per second is unit for velocity, meter per second square is unit for acceleration. So then this is my acceleration. Now, why is acceleration is negative? Well, because object is slowing down. So every time the object moving in one direction, that means let's say it has a positive velocity, if it's slowing down, then acceleration will always then be in the opposite direction. That's kind of how it always works. Because what the acceleration because you have to slow down, acceleration tells you that every second you change your velocity by 2 meters per second, but negative direction means that you are slowing down. If acceleration here would have been positive and you're moving in a positive direction, then you would be actually speeding up rather than slow down. So that's some of the things that you guys should try to remember. If you're slowing down, that means acceleration always in the opposite direction of the velocity. Velocity is positive, acceleration negative. If you're moving to the left and slowing down, it means velocity is negative, acceleration is positive. So in a way, it's not necessarily if you're slowing down, acceleration has to be negative. No, acceleration is in the opposite direction. That's why you're slowing down. All right, so let's look at one more example here. How long does it take a car to cross a 30-meter wide intersection after the light turns green if the car accelerates from rest at the constant rate of 2 meters per second square, which is a constant acceleration? Again, let's see what we're given. We're given that car crosses 30-meter wide intersection in a way which means that I can take x initial. By the way, the initial sometimes can be written as x sub I or x sub 0. That does the same notation, just different notation, but meaning same thing. So this is 0. X final, then 30 meters. We are told that the car accelerates from rest. What does it mean? Well, it means that it was at rest to start with. That means initial velocity here is 0. Now, after that, then what we have here is we're given that also that acceleration is 2 meters per second square. Right. And what we want to find, we want to find basically how long does it take. That means we want to find the time. Now, here's what I have. You look at what's given to you, and then you look at those three kinematic equations. V final equals V initial plus AT. Equation 2, X final equals X initial plus V initial times time plus 1/2 AT squared. Equation 3, V final square equals V initial square plus 2A delta X, for example. And then equation 4, delta X is equals to V initial plus V final over 2 times time. The idea here is this. The reason we have 4 equations, because we have a lot of variables. See, we have, X initial, X final, V initial, V final, acceleration, and time. We have 6 variables. So does it mean that, we can have one equation and have all of those variables? No, we're going to be stuck a lot of times. So that's why we have 6 variables, and we have technically at least 3 equations that can help us. The fourth one is kind of bonus one, but the idea here is that more equations we have, better for us. Remember, if you have one unknown, all you need is one equation. If you have 2 unknowns, then you need at least 2 equations. 3 unknowns, you need 3 equations, and so on and so forth. So that's why. Also, one of the things we have here, if you look at those equations for the kinematic equations, right? Each one is a little bit unique in a way that each equation is independent of at least one quantity from, those kinematic variables. Let's look at equation 1. Equation 1 has V final, V initial, acceleration, and time, but it doesn't have the displacement, which means it's independent of the displacement. If you're not given displacement, it's okay. You can use that equation. Equation 2, X final, X initial, V initial, acceleration, and time. It is also independent of at least one variable, and that variable, if you look at it, you will see is V final. Equation 3, V final, V initial, acceleration, delta X. Well, what's missing is time. That means it's time independent. If you're not given time, you can still use equation. Equation 4, basically independent of acceleration, but we can assume that you technically have an acceleration, let's say. That means your goal will be to read the problem twice, write down what's given to you, then you look at your equation set and see which one you can use to solve the problem. So in this case, look at it. You're given initial position, initial final position, initial velocity, acceleration, and you need to find the time. All right, so there are 3 equations with time. Equation 1, equation 3, equation 2, and equation 4. Can I use equation 1 to find the time? Think about it. Well, you can't, because in this equation, if the time is one thing is unknown, everything else should be given, but we don't have V final, which means same thing in this equation 4. You have time and V final, 2 unknowns. That means we can't use this and we can't use that. How about equation 2? Well, equation 2 tells you that there's a time, which is unknown, but then it requires you to have X final, X initial, V initial, and acceleration, which we have all of those, and it doesn't even include V final, which we don't. That means, we're good to go. That's the equation that we need. So then what we do here is we go and use that equation. Delta, X final equals X initial plus V initial times time plus then 1/2 AT squared. All right, so that's the equation. You can then simplify because X initial is 0. So this how I represent something is 0. Well, V initial is 0. That means this whole term is also 0. That means what we end up with is X final equals then 1/2 AT squared. Well, I then rearrange and just solve for T, which is going to give me T is equals to 2 times X final divided by A, but since T is squared, square root. Which means then all I have to do here is then go and calculate, plug in all the values, right? 30 for the X final, 2 for the acceleration, and we're going to get 5.5 seconds. So that's how you approach this type of kinematic problems. You write down what's given to you, what you need to find, then you look at which equation can work, eliminate what's 0, what's constant, and things like that, and then solve for the unknown.